Modeling, Simulating, and Measuring Car Suspensions by Mitch Frasca. In this presentation, I will cover the following topics: a brief overview of car suspension systems, including their importance, their main components, and how to optimize them; in-depth modeling and simulation of the suspension system, where I will show you how I modeled and simulated the test car; experimental data collection, where I gathered a set of points in order to compare my simulation data with my experimental data; and finally, utilizing results, where I will analyze my simulation, measurements, and modeling in order to reflect on what things I did right and what things I did wrong. Section 1. Brief overview of car suspension systems. Importance. Why car suspension systems are important. First of all, they maximize grip between the tires and the road. Second, they improve cornering. Third, they minimize movement of the driver compartment, ensuring a good ride for both the driver and any cargo that he might be bringing along. Basic components. Coil springs. Coil springs provide the upward force on the car from the wheels. They absorb forces from the bumps on the road, and they also ensure constant contact with the road by forcing the wheels down. Optimization of coil springs. When implementing a coil spring, the designer has one of two things in mind: comfort or performance. In order to maximize comfort, less stiff coil springs can be utilized in order to displace more, henceforth absorbing more shock and displacing it from the car. If performance is desired, stiffer coil springs ensure a maximized contact with the road, as well as increased responsiveness to the driver. The second basic component is the shock absorber. The shock absorber acts as a piston cylinder device with a hydraulic fluid in the middle. When the wheel is displaced, the piston is forced through the hydraulic fluid, and the hydraulic fluid converts kinetic energy into thermal energy through resistance. Section 2. Modeling and simulation of a suspension system. Creating a model. The half-car model is different from the models that we use in class because it has 2 degrees of freedom. It both moves in the theta direction, rotation of the car, and the x direction, raising and lowering of the car. The inputs of the half-car model can be represented as x1t and x2t, which are all the displacements stretching and compressing a spring and a damper on each end. This spring and damper represents the suspension system. First, we will analyze the system with static analysis. Through static analysis, we can find the force that will be constantly applied from the wheels to the car due to gravity. In this system, there are 3 forces. FGF, representing the force from the front wheels due to gravity. mg, the force of gravity acting on the mass of the car. And FGR, the force of the rear wheels to the car due to gravity. We can find this FGR by summing the moments at the left axle. Here is the equation derived. By summing all the forces in the z direction with this newly found FGR, we can solve for FGF too. Now we will move to analyzing the spring dampers and finding the force that they act on the mass. So here is a zoomed in view of the node of the top of the spring damper in between the mass and the spring damper itself. Kx represents the force of the spring on this node. Ff represents the force of this node on the car. Fgf represents the force of this node on the car due to gravity. This is separate from Ff. This is an additional force. And B times x dot represents the force of the damper on the node. By summing the forces in the x direction and recognizing that the mass of the node equals 0, we can easily solve for the force of each node acting on the car for both the front wheel and the rear wheel. Now that we have these equations for force acting on the car, we must find xf, x dot f, xr, and x dot r. The x's, in this case, are a sum of the motions which cause the spring damper system to stretch. Each of these equations must account for displacement vertically of the car, displacement vertically of the road, and displacement with regards to pitch. Note, the values of displacement with regards to pitch utilize the small angle assumption. This is why there are no signs in these equations. Finally, we will look at the car with kinematic analysis. We will sum the moments of the car at the center of gravity. This is equal to moment of inertia times angular acceleration, or the moments of each force acting on the car. The moment of inertia can be solved for using this basic equation here, where h tot equals the total height and h axle equals the height of the axle, meaning that we're accounting for the main mass square of the car. To find the z acceleration, we simply do a summation of forces in the z direction equation. Now I will go over the values that I used in these equations. The following equations are parameters that were provided by the manufacturer on their website: car mass, wheelbase, height of car, height of axle. Other parameters that I utilized were acceleration due to gravity and height of the road, which I modeled in Simulink. In order to find semi-accurate spring constants and damping constants, I looked on the internet for average spring constants and damping constants. I will now go over the closed loop system that I created in Simulink in order to simulate this system. You will first notice that everything rotates around these two masks. These masks represent the equations that use the spring damper system. This includes the forces of the front and rear wheels on the car, as well as the solutions for theta double dot and z double dot. Looking at the front spring damper system. Here, input are theta, theta dot, z minus h1, and z dot minus h1 dot. They are put through the same equation that we used to find the front force earlier in this section. Additionally, the force of gravity F is added. Output is the moment of F and the force of F. Similarly, the equations for the rear system are used in order to find the force rear and the moment from the rear. Now you can see that we solve for theta double dot using the masks, differentiate theta double dot twice, and we get theta, one of the values that we're looking for in our system. This is now fed back into the mask for the closed system loop. Similarly, we solve for z double dot and differentiate twice and solve for z. Over here are the inputs for h1, h1 dot, h2, and h2 dot, the displacements from the road. These can be edited with values in MATLAB. So now in the MATLAB file, we can see these are all the values that I previously defined in this section. Additionally, we can enter car velocity here for any experimental data or any velocity that we're curious about. Here, we can use a guessed speed bump height or one from an experiment like we will have in section 3. Finally, here, we can edit and check different spring constants and damping constants. Down here is just simply a graph of what I just showed. After running the section, we can see graphs of the displacement of the car and the rotation of the car. Procedure. Note: for this presentation, I will only be showing one dataset. This is because this is to serve as an example and to show whether or not the shape of my simulation was correct. First, the dimensions of the speed bump were measured. Second, markers were placed on the test car to track its motion. Third, the slow motion camera was set up such that it could view the car in its full displacement path. Finally, the car was driven over the bump at varying controlled speeds. A displacement value was measured at every 5 frames. Here, time is calculated using the current frame minus the initial frame divided by the frames per second. Here is the original displacement versus time graph, which I got straight from the data that I collected. One thing that you may notice is that the lowest valley is barely under 0 displacement. This is because the road that I measured on had a large curve that was sort of parabolic, so it was causing all the information in the middle to be plotted very far up. In order to make this data useful, what I did was I collected the height of the wheels, which is as close as I could get to the height of the road, at every 5 frames for the entire clip. And using this data, I calculated the height of both wheels, and then with both wheels' height, I could calculate the road's curve effect on the center of mass displacement of the car, which is right here. Now, once you take the original data and subtract it by that displacement, you get a little bit nicer of a graph right here. Now, reviewing the sample video, one very noticeable thing is that the graph, or the measurement grid, has a constant decline. This is because the car was slightly moving away from the camera as it drove. So I had to scale each graph for the height of the markers. Finally, you may also notice that the video is rotated. This is because the road also had an incline. Comparing results. Here I have 2 displacement versus time graphs. The top displacement versus time graph is gathered from our experimental data, where the bottom one is measured with Simulink at the same exact speed. One thing notable is that the apexes are actually pretty similar. This is a good sign for our estimation of K value. Although you may notice that this is lower, which means that most likely the car's actual K value is lower, meaning that it displaces less energy into the car, raising it less. An additional thing to note is that each graph has similar peaks and valleys. This is a good sign. This means that our Simulink model is at least giving us the right shape, although it can be kind of hard to tell whether or not the frequency is correct. Error analysis. So there are many reasons why there could be error between these plots, and so it makes sense that there is a large margin of error. So for the simulation, assumptions like the car being a box, the wheels having no mass, and the suspension acting like a perfect spring damper system will most certainly have an effect. Additionally, predicted values like the center of gravity could be off. For data collection, irregular bumps and curves were on the road, and imprecise measurement tools, such as the camera not being positioned perfectly, can affect the quality of the data. Conclusion and recommendations. This project has been successful because I created an accurate simulation. Additionally, the variables can easily be changed, allowing it to simulate any half-car model and be modified for any input. The model with predicted values had the same general shape and size as the experimental values. This is a good sign for the accuracy of our predicted values and also the model. MATLAB and Simulink are extremely powerful tools because they can model a wide range of reactions of multi-degree of freedom systems. Recommendation. Recommendations. I have 2 recommendations that I feel would help anybody who is trying to model a system the way that I did. First, when recording complex systems with video equipment, it is extremely important to eliminate disturbances such as bumps. Measure as precisely as possible, because error is common. When creating simulations, if the outputs skew to infinity, look for sign errors. I had a couple issues while designing my project where a sign error was causing everything just to go to infinity. This turned out to be like a negative sign. And these are my sources. Thank you.